Welcome back. The final in my series today of videos that deal with the energy topic at GCSE is to deal with bond energies. Now, as the name suggests, bond energies deal with the energy that each covalent bond has when either we're trying to make it or break it. And these are so very useful. They are a great way to sit on your backside and work out the energy change for a reaction without having to do it. And you get pretty close results. So it's a good method. But you've got to bear in mind, because we use average bond energies, then the answers are slightly out. Small error, but definitely nowhere near the error that we got on those blessed combustion experiments. Anyway, let's get into this topic, the bond energy topic within energy. And I want to start with a reaction that I hope you're all familiar with, the burning of hydrogen. If you take hydrogen and oxygen and react them together, like burning hydrogen in air, that's what happens. The oxygen in air reacts with the hydrogen that's burning and it makes steam for you. Hydrogen gas molecules react with oxygen gas molecules to make steam. Now, in this topic, it's vital that you understand chemical reactions are all about breaking the bonds which exist in our reactants and then making new bonds that are needed to keep our products together. So existing bonds are broken, new bonds are made. I can show you this visually. Can we look at the balancing? 2 hydrogens, 2 steam. In terms of moles, that is the balancing. But I want to show you using Mollimod models. So these are the Mollimod molecular models kits. H2 hydrogen, H2 hydrogen, 2 of them, because we need to balance it with the 2 oxygen. Oxygen gas is doubly bonded, double bond oxygen, and therefore we want to turn those into water. Well, every single chemical reaction can be thought of as starting with those chemicals, reactants, turning into products. Can you see there's 2 red balls, 4 white balls, 4 white balls. The 2 red represent oxygen, the 4 white represent hydrogen. And if I want to turn those into those, I then have to take these bonds and break them. I have to break existing bonds. Like that. Having broken them, then I can put them together. I can put them together by attaching them like that. And what am I making? Well, what I'm making are 4 of these. Look, that's water. There, water, 2 of them. I've just pulled apart existing bonds and made 4 new bonds like this to make the water molecules I have left as products. So all reactions can be thought of like that. Back to my PowerPoint, I was trying to explain this and I've demonstrated the Mollimod version of that reaction. I'm now going to draw it out so that you can recognize a small stick is a covalent bond. So 2 hydrogens, an oxygen, 2 waters, 2 moles of hydrogen, 1 mole of oxygen and 2 moles of water are made. What we're breaking? Well, we're breaking 2 moles of hydrogen bonds. Look, one bond there, but they're moles. So 2 moles of hydrogen. And we need to break that oxygen double bond oxygen. We need to break a oxygen double bond oxygen. And we need to make 4 lots of these oxygen hydrogen bonds. Now, would it not be great if you knew the energy values that are needed to break those bonds, and you knew the energy values for making those 4 new bonds? Then you could sit on your backside and work it out without having to do that practical. Well, there do exist things called average bond enthalpies, or average bond energies, or mean bond enthalpies, energies, or mean bond dissociation energies, or mean average bond dissociation. Anyway, look, there's a load of words. Mean and average fundamentally mean the same thing. Bond energy, bond enthalpy, bond dissociation fundamentally all mean the same thing. So whatever combination they use, they're talking about the average energy needed to make or break a particular covalent bond. Now, they can be found in data books. I'm going to give you a table next on the next slide. On exams, they might give you a table, but sometimes they give you the data in a sentence in a question that you need for that question. The energies listed are average values, and they are per making 1 mole of a particular bond. The following slide lists such a table. Values are in kilojoules. Let's have a look. There, look. Oxygen hydrogen bond, hydrogen chlorine bond, silicon carbon bond, carbon triple bond oxygen. Now, I know you might think that these things, you've never come across some of them, so you're only going to need some of those, and that's why they selectively give you what you need for that question. Let's run through some really important points. To break existing bonds, we're talking about bond breaking, energy has to be put in, and that energy has to come from somewhere. Now, you might have to give it a Bunsen burner, etc. Remember our ideas of activation energy? In the activation energy section, we are breaking bonds. So bond breaking is endothermic. Bond breaking, energy goes in. The opposite of bond breaking is when new chemical bonds are made. When new chemical bonds are made, then heat energy is given out. And when heat energy is given out, that reaction is exothermic. So bond making is exothermic. If bond breaking is endothermic, bond making is exothermic, for a reaction, every reaction, there's a bond breaking element to the reaction, followed by a bond making element to the reaction. What if we subtract these values? If we subtract B from A, then that's that, take away that. That's the energy coming out, and that's the energy going in. The difference will give you the energy change for the reaction. If we subtract, then the difference is the overall energy change for the reaction. If you do it in that order, energy in minus energy out, then you get the right sign. So if it's exothermic, it'll be negative. If it's endothermic, it'll be positive. If you do it that way around, A minus B. If you do it the wrong way around, you get the wrong sign. The value will be the same, but the sign will be different. I'm going to take you through 2 worked examples. Firstly, the Molly-Mod demonstration of burning hydrogen. Watch. There's the reaction. Those red bonds are being broken. Those red bonds are being made. And I've used the table to give me a value of hydrogen, which is 436. Multiplied it by 2. So you've got 2 there, 2 lots of it. Compared to oxygen, you only want to break 1 mole of oxygen. It requires that much. That is energy going in. And this is energy coming out. Energy going in is those two added together, 1370 kilojoules. Making new bonds, energy comes out. Energy comes out is 4 lots of those. Energy comes out is that much. So if you do it that way around, energy in, take away energy out, then look, there's more energy coming out than going in, so it's a minus 482 kilojoules per mole. When you're working out delta H values, they must be positive or negative. And they must be per the number of moles that are in that equation. So always the kilojoules per mole represents kilojoules is the energy change for the moles in that equation. Per mole means per the moles in the equation. Example 2. You don't always have to break all of the existing bonds and make all of the new bonds that are made. Obviously, some bonds are broken, but not all of the bonds are broken. So if you can identify which bonds are broken, then just break those. And then if you can identify which new bonds are made, just make those. So in this example, propanone reacts with hydrogen gas and it makes propan2ol. And ignore that. Ignore that for now. That's a leftover from my calculation, which somehow is remained there. Don't worry. Let's just deal with what's breaking and what's being made. CH3, bond C, bond CH3. CH3, bond C, bond CH3. That row of atoms, that sequencing stays before and after. If it's there before and after, nothing is breaking or being made in that sequence. What's being broken here is just that. Carbon double bond oxygen is being broken. So if we're talking about energy going in to break bonds, we only need to break that one bond. And what new bonds are being made here? Well, that's new. The hydrogen carbon is new. The carbon oxygen is new. And the oxygen hydrogen that I'm pointing to, that is new. Let's put those in. To break, you have to break just that red one. To make, you have to just make those red 3. And then in blue, I've got the values. That bond has a value of 745 kilojoules. And that is energy that needs to go in. Energy needs to go in. 755 kilojoules needs to go in to break the carbon double bond oxygen bond. Well, what about this side? Well, that's energy out. And 3 bonds, the new bonds that are made, are that, and that. And on a data table, I've looked them up, and I get 1, 2, 3, 4. 1,234. So what's my overall enthalpy change? Well, it'll be the difference between those. Energy in minus energy out. Look, 745 is energy in, minus energy out. It ends up being exothermic because it's negative 489 kilojoules per mole. Now that's example 2. Example 3. I'm not going to work this one out, but I want you to see, and I want you to link what we've done with bonds, bond energy. I want you to link that with energy profile, energy diagrams, profile energy diagrams, and rather than pick a general one, I picked one where methane is burning. There's methane and oxygen. You burn it, and it goes through that kind of profile. This upward, the activation energy, is when bonds are being broken. So existing bonds breaking is the red. And then the new bonds being made is the blue. Energy released on bond formation. Energy required to break bonds. The red and the blue are red is the input, blue is the output. So if that much energy goes in, that much energy comes out, that's bigger, and therefore it's going to be exothermic. That there is the enthalpy change. That there is the energy change. Look, it's labelled energy change, delta H. And that energy comes out to the surroundings. I've been whittering on like this about all kinds of examples. So, in all of these energy level diagrams, you can think of the upward movement as energy in to break existing bonds, and the downward arrow afterwards as energy out to make the new bonds. And if the downward arrow is smaller, then it'll be endothermic, because more energy will have to go in, less energy will come out, and therefore it will require energy overall. The energy will go in from the surroundings, which get colder, and those reactions only happen when there's a favourable entropy change, more disorder happens. So, what do I want you to do now? Well, believe it or not, it's this. Practice. Practice doing lots of examples, until you get them correct. This is like mathematical topic, especially the work on bond energies. Unless you do maths type things over and over again so they become second nature, then you'll make mistakes in an exam. If you want to be good, practice. Practice makes perfect. Right, that's the end of the energy topic. It's taken me all day to do that, but at least I've started and finished in a day, the energy topic. Good luck. Next time I'm going to deal with the rates topic.